Evacuating along the India-Bangladesh border. They're trying to get to safety ahead of super cyclone Amphan. This is the strongest storm ever recorded in the Bay of Bengal. Yesterday, it was packing winds of up to 270 kilometers an hour. It is expected to make landfall Wednesday evening. India's disaster response team that you can see here is warning people with loudspeakers there, bullhorns, to evacuate. Get out of the way. This is happening near the Indian city of Kolkata, home to more than 14 million people. CNN meteorologist Chad Myers joins me now live from Atlanta. So let's talk a little bit about how big of an evacuation zone here are we talking about?
I would say, Hala, anyone that lives within, let's say, 10 meters of sea level, you're going to have to get out of the way. I know we're talking about a 5-meter surge, but you're also going to have waves on top of that 5-meter surge. So anyone that's living right along the shore, right along sea level, will need to get away. Yesterday, when we talked, this was a 270 kilometer per hour storm, the strongest storm ever in the Bay of Bengal. Now it is not. Now it's 185. It has lost some intensity, but it has not lost its storm surge. That bubble of water is still under this storm, and it's going to make landfall in a very low-lying area. People moving away from the land, moving away from the ocean. Now, when you get to a wind like this, 130, the rule of thumb is something like hide from the wind, run from the water. So if you can get away from the wind and hunker down somewhere, you're great. But if you're within that 10 meters of actually the sea level, you need to get out of there. And there it is, making landfall tomorrow, probably in around 24 hours or so. We will see this 4 to 5 meter storm surge right into this delta, and many, many people, Hala, are going to be in the way of this water. And it's really, really hard, I suppose, to stay 6 feet or 2 meters away from anybody else when you're in a bus trying to get away from this thing.
When I got back, I knew something was wrong.
So now let's have a look here at our live time and weather map. So remember, you used this website for an activity where you were determining wind speed, temperature, and ocean currents around the world. So now we can have a look here at this cyclone that is about to hit off of the coast of India and the Bay of Bengal. So remember that a cyclone is the same thing as a hurricane. It's the same thing as a typhoon. But the name just depends on the region of the world that it encompasses. But it's the same natural process where you have a low pressure zone will form, and you will have the sea surface temperature raise to where you have a rotation of air spiraling around the eye. So here you can see it is the eye of the cyclone. So if we want, we can click and see the temperature here, as well as the speed. So right here we're looking at a speed of about 88 kilometers per hour, or we can change that to miles per hour. So it's getting pretty close now. It's about to make landfall, and it's about 11:45 p.m. here as I'm giving this lecture. So just a little bit of a current events application for you to see how important it is that we have meteorologists, climatologists who are tracking these types of events such as hurricanes and cyclones, and making sure that the appropriate populations are evacuated from the danger zone. So once again, this is a live time map. So if ever at any point in the future you want to do the same job as a weather person and study how storms are occurring across the world here, you can always come back to this website, Earth at Null School. So this lecture will cover ocean waves, and we'll discuss several things about them. So first of all, how do waves form? But more importantly, what exactly is a wave? How do we define the different elements of a wave? And how does that information determine when a wave will break and the pattern that waves display as they approach the shoreline? So, as you've seen in your introduction video on YouTube, waves are the result of a disturbing force. So, i.e., waves are created by a release of energy. So, this is one thing that often confuses students, is that when we think of waves, we don't tend to think of them as energy. But physically, if you're standing at a point bar in the ocean and you witness a certain number of waves, you're not actually seeing that water moving. What you're seeing is that energy is propagating through the fluid and displacing it. So waves are created by a release of some type of energy or a disturbance. So you need a disturbance first. So those types of disturbances include wind, also the movement of fluids of different densities. We also get things like landslides or mass movement into the ocean, underwater seafloor movement from things like tsunamis, so where you would get an earthquake and the seafloor would become displaced from the slip along that fault. You would generate something called a tsunami. We also have the pull of the oceans from the moon and the sun, which are known as tides. And we'll cover tides in the next lecture. And of course, to a very small degree, human activities can generate waves as well. So every wave begins with a disturbing force, right? So this causes the waves to form. And wind is the major one, right? So wind blowing across the ocean surface is imparting energy to the ocean surface. And that wave will occur along something called an interface. So that can be three different types, right? We have an air-ocean interface. These are known as ocean waves. So this is where our ocean contacts the atmosphere. We also have air-air wave. We also have an air-air interface. And along this interface, we generate something called atmospheric waves. And then deeper down into the ocean, you'll have waters of different density. And so you get something called a water interface. And those waves are called internal waves. So we can have a look at that here. At the surface, we have the wind generated surface waves. The wind is imparting that energy to the surface. But then within the ocean column, we have low density water that sits on top of higher density water. And so that energy is imparted along that interface. So waves occur along interfaces. So those are known as internal waves here and surface waves up at the top. So looking at just internal waves, these are much larger than surface waves. And these waves are caused by things like the tides, turbidity currents, which are those submarine avalanches that you sometimes get off of the coast, as well as wind and ships. And they're a real hazard for submarines. So it's very important that the ship's captain and the crew have an understanding of these different interfaces and depths and densities in order to determine the internal waves for their navigation. Some other types of waves include splash waves. So we get these from things like coastal landslides or calving icebergs. We get seismic sea waves, also known as tsunamis, from seafloor movement. So one piece of seafloor moving up relative to another along a fault. Tides, which are a result of the gravitational attraction between the moon, sun, and earth. And we also get the wake from ships as a type of wave. This chart here shows the amount of energy that is the result of the majority of waves generated. So you can see here we have wave energy on the x-axis and wave period on the y-axis. So wind causes wind-generated waves, and you can see that's the majority. Roughly 70% of all waves are wind-generated. Then we get waves generated from things like earthquakes or submarine volcanoes and landslides or storms, which can generate waves called tsunami. And then we also have the contribution from the gravity of the moon and the sun, which actually physically pull on our oceans, and that generates the tides. So that's the smallest amount here, and the majority of waves are generated by wind. So when we talk about waves, water is not the only thing that harbors waves. Anything that can transmit energy will be associated with waves. So remember when we talked about earthquakes, we discussed the different types of waves. Earthquakes are a wave of energy that is moving through the earth, and that shaking you feel is the release of that energy. So when you have movement of two geologic pieces along a fault, like the San Andreas Fault, if that fault slips, you're going to release the energy that was stored up in that rock for however many years it went without an earthquake. And as energy passes through the rocks, you feel the shaking. So you feel that energy release. So when we talk about ocean waves, we can compare that. There's three main types of progressive waves. The first is longitudinal, which is associated with back and forth motion. So you can think of that as if you were squeezing together a slinky and then re-extending a slinky. Whereas a transverse wave is a side-to-side motion. So particles move back and forth at right angles to the direction of energy transmission, or the path that the energy is moving. And these waves can only go through or transmit through solids, so they cannot transmit through liquids. Orbital waves are a combination of these two, of both longitudinal and transverse. And so they move in an orbital motion or an orbital path, and they transmit energy along the interface between two fluids of different density, i.e. liquids and or gases. So ocean waves are orbital waves. They are a combination of both longitudinal and transverse waves. So when we talk about a wave, and you saw this introduced in the first YouTube video, we can define the parameters of a wave with different variables. And in the next couple slides, we're going to use those variables to determine things like wave speed and when a wave will break. So let's review these vocabulary words here. The crest of a wave, you can see here, that is the point at the apex or the top of that wave, whereas the trough is the bottom here. So you can see that labeled trough. So here's your crest. It's the top part of the wave. The trough is the bottom part of the wave. And the wave height, H, will be the distance from the wave trough, the height from the trough to the crest. Right? So you can see that labeled here, wave height. The wavelength, which is L, will be the distance between two crests. Right? So you can see that this is one wave here. So the length would be from crest to crest. Still water level is this red line, and that represents where the water would fall without the disturbing force that's causing the waves. And then you can see the orbital motion reflected in these orbital arrows here. So notice that they're getting smaller and smaller with depth. And that's because you are getting further and further away from the wind energy, right? So the wind is striking at the surface, so you're going to have the most disturbing force at the surface. But the deeper down you go, the further away you are from that energy, until you reach negligible water movement at half the wavelength. So whatever the wavelength is, you will have negligible water movement below half of that distance. So if your wavelength is 20 meters, then that means that as soon as you approached 10 meters in depth, you'd have negligible wave movement. So now we can calculate something called wave steepness. So steepness, you can remember, is also known as slope or rise over run, right? That this is explaining how a curve can be more or less flat. So if you have a curve that is has a small slope or a flat slope, its rise over run will be close to zero. So when you look at the wave steepness, you can calculate the wave height over the wave length. And if the wave steepness exceeds 1/7, then the wave will break. And so when we look at the physical constants of Earth, 1/7 is purely a function of the gravity of this planet. If you went to a different planet in the Andromeda galaxy, which had a different gravity, this ratio would be different. Right? So this is purely a function of the gravity of our planet. And if you've ever seen the movie Interstellar, you'll remember there's that scene where they go to this planet and the wave is very large. It's the size of a skyscraper, but the water is very shallow. And that's a result of, they mentioned, the gravity is significantly different on that planet than Earth. And you remember Anne Hathaway, she's huffing and puffing because of that. So, period, when we look at the time constraint, we define a variable called t, which is the period. And that's the time it takes one full wave or one wavelength, one crest to crest, to pass a fixed position. And this is going to be very useful to sailors and captains out on the ocean who need to calculate the size of waves. They need to know these types of constraints. So this illustration here demonstrates the circular orbital motion of ocean waves. So as a wave travels, the water passes the energy along by moving in a circular orbit. So the floating objects, such as this rubber ducky, will also follow circular orbits. So you can see here at time A, you have the wave movement is towards the shore, and the ducky moves up and backward. Then he moves up and forward, down and forward, and then finally down and backwards. And this may have been something that you may have noticed before when you were at the beach, and you're just floating. You may have felt before that you're sort of stirring in a circular motion. You're sloshing back and forth. You're experiencing the circular orbital motion associated with ocean waves. And when we look at that orbital motion, remember that size decreases with depth until it's about zero at something called the wave base. So the wave base is this green line here, and below that you have negligible or no water movement. So we can look at these parameters again. Here we have one wavelength and 1/2 of a wavelength. So we can use that to determine how deep we would need to go before we would see negligible water movement. So this is going to be really important for ocean navigation, is measuring the amplitude and the wavelength of the sea conditions. And we also have to look at the different types of waves looking at the depth. So we have a couple different vocabulary words. Deep water waves are where the water depth is greater than the wave base. Shallow water waves are where you have a water depth that's less than 1/20th of the wavelength. And then we also have transitional waves where the water depth is less than the wave base, but it's also greater than 1/20th of the wavelength. So we have these criteria to determine the different types of waves based on their depth relative to their wavelength. If we want to determine wave speed, then we have set equations for that. So wave speed is also known as celerity, and it's going to be proportional to the wavelength. So if the oceanographer or the scientist can measure that wavelength here, then they can determine the speed. So this curve is a fixed value. So at sea, if they're looking to determine the speed, all they need to do is calculate the distance between two wave crests. And that can be achieved by any type of floating buoy and a stopwatch. When we look at shallow water waves, the celerity or the wave speed, instead, this is going to be proportional to the depth of the water. So that equation looks like this here. Wave speed will be equal to the wavelength over the wave period, right? So distance over time. So that's what we normally would see. So you can summarize it in this way here, but I won't ask you to do any math on your homework, so don't panic. But it's important for you to understand how these values are calculated and why we need to measure specific criteria and why they factor into decisions in ocean navigation. So waves themselves originate in a sea area. So we have some type of energy system. So here you can see we have this wind generating a storm here. And the direction of wave advance will be proportional or parallel to that disturbing force. So out here in the front of the storm, you have the swell. So basically that describes it describes the waves that have traveled out of their area of origination, right? So they've moved away from their original source and they exhibit a uniform and symmetrical shape. And when we look at that figure zoomed in here, right, you'll see there's a couple of vocabulary words here. So the red dashed line indicates the limits of the storm, and the storm moves whichever way along the energy propagation. And we just looked at the cyclone that's off the coast of India, and that track has been estimated based on the wind directions and ocean current directions, which path it's most likely to take, where is it going to make landfall. So measuring properties like the swell and the fetch is a word that describes the physical distance or the length of the storm. But in oceanography, we use a lot of different terminology for things such as distance or time. That's sort of a tradition for the nautical way of interpreting things. So wave height is directly related to wave energy. And wave heights on Earth are usually less than 2 meters or 6.6 feet. Breakers called whitecaps form when waves reach critical steepness. So if you're at the beach, I'm sure you've seen this before where you have a wave that's about to break, the topmost part will turn white. And so those are called whitecaps, and that's when the wave is reaching its critical steepness and it will break in the next moment. And we have a scale known as the Beaufort wind scale that describes the appearance of the sea surface. And this is what you'll see the meteorologists using on the Weather Channel, right? When they're describing a specific type of wind. You may have heard before a gale force winds or storms or hurricanes. I'm sure you've heard the word breeze before, right? So these aren't casual terms. They correspond to specific descriptions in wind speed, as well as the appearance of the sea. So for example, if you had a Beaufort number of 0, we'd say it was calm and wind speed would be less than 1 mile per hour. A gale force wind would be 39 to 46 miles per hour, and you're going to see moderately high waves of greater length. Edges of crest begin to break into spin drift. Foam is blown into well-marked streaks. And then, of course, you have the hurricane, which is what's occurring right now with the Amphan cyclone. The air is filled with foam and spray. The sea is completely white with driving spray, and visibility is greatly reduced. And you get wind speeds of 73 miles per hour and up. So I think we saw a wind speed of about 74 when we were on the Null School website looking at the Amphan cyclone. So when we look at global wave heights, this scale here indicates the height in meters. So red being the highest waves, or up to 6 meters in height, blue and purple being the shortest height waves. So we can see here that around the South Pole near Antarctica and south of Australia, we have the largest wave heights recorded. And there's a couple of reasons for that. So here we can see we have the oceanic conveyor belt. So there's a cold and salty deep ocean current that circulates through this region that's recording the highest wind speeds. So this area is known as the Southern Ocean and the Antarctic Circumpolar Current. And we studied this a little bit when we talked about ocean currents, but scientists have a really good grasp on why these waves are so big. It's a combination of consistent and high winds, as well as the open expanse of the ocean that basically creates an environment ideal for gigantic waves. The Southern Ocean itself, it's home to some of the largest waves in the entire world. And I remember when I was on the south coast of Australia, I was at the southernmost point, and the only thing between you and Antarctica was this ocean current. And I remember it was the windiest place I'd ever seen. It was really incredible. And the reason why winds are so intense down here near Antarctica in the Southern Ocean is because of the criteria that are necessary to generate large wave heights. So when we look here, one of those criteria is you need to have a lot of energy. The second is that energy needs to blow over a long surface. So the fetch has to be really large. So the longer period of time that energy is imparted over the longer distance, then you will generate larger waves. So looking at the largest waves ever recorded, in 1935, the vessel, the USS Ramapo, experienced large waves while crossing the Pacific Ocean. And it's pretty admirable that at the time they were able to record this wave height, because I don't know about you, but I would be pretty frightened to be witnessing this event. But the wave height was measured about 34 meters or 112 feet high. So this is achieved by using the angle between the eye height of the observer on the bridge and the stern of the ship in the trough. And so they were able to calculate that just based on a simple algebra equation. And so although this is the largest wave ever recorded, it's likely that waves on this planet can be probably larger than this, but nobody has lived to tell the tale or been able to record it in those types of conditions. So when we talk about waves, we also have to discuss what happens when waves meet. And I can use an analogy of a pond, where maybe you're at a pond with a couple of friends and you're all standing at different sides of the pond. Maybe you're standing over here, your friend is on the south side of the pond, your boyfriend's on the west side of the pond, your mom's on the east side of the pond. And the pond is calm and you all throw a pebble in at the same time. You're going to generate ripples, right? So here you've generated these ripples here, or no, that was your mom. And then your boyfriend generated the ripples here. Well, what happens when those ripples intersect? That's known as something called an interference pattern. And of course, in the ocean, you're going to see interference between waves. You're going to see waves moving in different directions that will collide and coalesce. And so there's 3 different types of events that can occur. You can have constructive interference, where you have 2 wave crests will meet, and that will increase the wave height. So it's called constructive. The second type is known as destructive, and this is where you would have 2 troughs meet. Or no, I'm sorry, you won't have two troughs. You will have a wave crest and a wave trough meet. So you're basically canceling out the wave, right? So constructive could be two crests or two troughs. Destructive would be a crest and a trough, and it would equal a flat sea like this here. But most waves are going to be mixed, right? You're never going to get a wave intersect exactly at the crest or exactly at the troughs. And where you would, you'd probably generate something significant. But most waves are mixed, right? So they have a variable pattern. So they look something more like this. So that analogy here of the pebbles in the pond is a good one for looking at what occurs in the ocean, because we have a lot of different disturbing forces that will interact with each other. And when we want to talk about something called rogue waves, we can look at the interference patterns. So rogue waves are a very special type of wave. And basically, they're very mysterious because they are these really large waves that seemingly appear out of nowhere, right? So it could be a completely calm day. You're not in a storm or anything like that. There's no earthquake. And all of a sudden, you're out on your boat and this huge wave appears. And scientists don't understand them that well. And a lot of work has been considered in the Bermuda Triangle. You may know that that is a region of the world that's very chaotic for sailors. And so the best estimate for these rogue waves, and you can have a look at these videos here, they're the top 5 rogue waves caught on camera. It's pretty spectacular. People are just going about their business on a beach, and then all of a sudden this huge wave overtakes them. But basically the hypothesis is that it's some type of favorable combination of constructive interference where you'd have 3 or 4 or however many waves, depending on the height of the rogue wave, all intersect at a perfect crest. And so this large wave would seemingly appear out of nowhere because of the intersection of a certain number of these crests. And the Bermuda Triangle may be a place where those conditions seem to be more active. So studying those interference patterns can better help with looking at things for seafaring navigation. So now let's take a closer look to what happens to waves in something called the surf zone. So out in the deep ocean, you may know that waves are different. They're fundamentally different because at the shoreline, you see waves breaking, and they're always breaking parallel to the shoreline, right? They're not breaking at a 90-degree angle. They're always coming straight towards you. And there's a reason for that. It's because waves undergo physical changes as they approach the shoreline in the surf zone. When we look at the changes that occur as a wave approaches the shore, the most important thing for you to remember is that it's related to the change in the wave base. So as you approach the shoreline, you're approaching the continental shelf. Remember, you're transitioning from true oceanic crust, which is much thinner than continental crust, remember, which is much thicker. So as you approach the shoreline or the edge of a continent, that height difference is going to cause the physical changes we see in the surf zone. So as a deep water wave becomes a shallow water wave, the wave speed decreases. So you can see that represented here. Velocity decreases. Because of that wave speed decrease, the wavelength will decrease. So we can see here that out in the deep ocean, we have the wave base is at a shorter depth than the total height or the total ocean column. So when we look at the wave as it approaches the shoreline, you can see that the wave base gets cut off here. And so the wave now begins to touch the bottom, or it feels the bottom here. And so because of that, the wavelength will shorten and the wave height will increase. Wave steepness, remember, is the ratio of the height or the wave height over the wavelength. And that steepness will increase as you approach the shoreline. When that steepness becomes greater than or equal to 1/7, the wave will break. And so that's why you always see this along the shoreline and you see these white caps forming in the surf zone. It's because of that velocity decrease represented as waves begin to touch the bottom and the wave base becomes cut off. So you can see that blown up here. Remember that the depth of negligible water movement is 1/2 of the wavelength, and that's known as the wave base. So as you approach the shoreline, the wave touches the bottom, and that surf zone is generated from the velocity decrease. When we look at breakers, we can define 3 different types. So we have spilling breakers, which are associated with gentle beach slopes. And this allows the waves to disperse their energy more gradually. Plunging breakers are moderately steep beach slopes, and it gives waves a curling shape that propels surfers. The third type is called surging breakers, and they're the result of the abrupt beach slope. So when we look at the steepness of a beach, we can determine subsequently what the waves will look like. If you have a gentle slope beach, you're going to create spilling breakers. If you have an abrupt slope beach, you're going to have waves breaking rapidly at the shore, and those are known as surging breakers. So looking at the geology or looking at the slope of that shoreline will indicate to you the types of waves that will be generated. Because remember, the slope of that shoreline is what is contributing towards the physical changes in the surf zone. So another really important thing for you to remember about waves in the surf zone is something that's called wave refraction. And this is the bending of waves as they move closer and closer to the shoreline. So I mentioned this before, but if you are standing at the edge of the shoreline here in the sand, the waves will always appear to break towards you, right? They're not breaking 90 degrees from you. And that's due to something called wave refraction. So remember, as waves approach the shore, the velocity decreases. Right, we saw that here, velocity decreases. So that means that part of the wave that's in shallower water is going to slow down, but the part of the wave that's in deeper water is going to continue on at its original speed. And so that discrepancy between the slowing of the waves in shallower water and the continuing of the speed of the waves in deeper water causes the waves to refract or bend, right? So that results in waves lining up nearly parallel to the shoreline, and the result is waves are more directly faced towards the shore. When we look at the shape of coastlines, the shape here is not a coincidence, and is also a factor of wave refraction. So wave energy is unevenly distributed on the shore. Orthogonal lines or wave rays can be drawn perpendicular to the wave crests. And we can see here that more energy is focused and released on the headlands than here in the bays. And as a result of that, you get this shape here, this sort of undulating shape. So because of that difference, waves will gradually erode the headlands, whereas fine-grained sediment will accumulate in bays. So that's why when you go to the beach, you are more likely to hang out in a spot like this, because you're getting sediment deposition and it's calmer, less energy. Whereas it would be a lot more dangerous going out to one of the headlands here where the energy is more concentrated and focused, and you're getting that active erosion with those wave cutting heights here. So we also have something called wave reflection. So before we were talking about refraction, but wave energy can also be reflected or bounced back when it hits a solid object. So for example, wave reflection produces large waves at a place called the Wedge near Newport Harbor in California. So you can see that reflected here. Waves can also be used as a source of energy. And they talked a little bit about this in the Ice and Fire documentary and how we can best use that in some of the windier regions of the planet, such as Scotland, because waves are associated with a large amount of energy, mostly with large storm waves. But of course, there's issues. How do we protect power plants? And also how to produce power consistently. And those accompanying environmental issues include building power plants close to shore, because those types of things will interfere with life as well as the sediment movement. And when you try to put a stop to or halt the natural sediment movement, you can also often create a larger disaster than previously was there. So here's a picture of a wave power plant and how that works here, the housing unit, the turbine, the generator. So the first commercial wave power plant began operating in 2000, so around 20 years ago. The Limpet 500, or the land-installed marine-powered energy transformer, is off the coast of Scotland and generates about 500 kilowatts of power under its peak operating capacity. So it's a promising area, but there's still a lot more that needs to go into the engineering side of things to make sure that normal sedimentary flow and biological habitats aren't interrupted that can have an even more negligible effect to begin with. So there's also wave farms in Portugal as of 2008 in the Ocean Power Delivery, which was the first wave farm. And about 50 wave power development projects globally at the current moment. So looking at this map here, we can see where it would be valuable for coastal wave energy resources. Looking at the wave height, so dark red being very high, wave height, look up to 3.9 meters, blue being very low or 1 meter in wave height. So you can see here some of the regions that could benefit from that type of construction here when we look at optimizing areas of large wave height. Okay, so now I have a video for you on the physical changes in the surf zone.
For thousands of miles, a wave has a perfectly regular, undulating shape. And then as the wave nears the shore, it rears up into a crest just before it breaks. Something has caused it to change.
And essentially what happens is, as it comes in towards the shore, it feels the presence of the beach that much more. And there is suddenly a great difference between what is happening at the top of the wave and what is happening at the bottom of the wave. Theoretically, what that does is that the wave at the top wants to move faster than the wave at the bottom, and that's what's causes this overturning. So the speed of the wave is dependent upon the depth. And for the most part, out in the ocean, the depth is so deep.
So that it's all moving at the same speed?
At the same speed. But when you come towards the shore,
the bottom slows down for some reason.
So the bottom has such an impact all of a sudden that the change in the height is crucial.
I was curious to see what happens when the energy of a wave dissipates, with the help, once again, of Professor McIntyre's rubber ducks.
Down there, it's mostly the energy which is moving.
Well, the energy is going much faster. See how much faster the crests are
I see,
than
yes, yeah.
ducks. That slow drift will take them close to the beach, and watch carefully from now on.
Oh, yeah.
That duck, look, suddenly it gets swept all the way up to the beach.
So
now that's where the wave motion becomes, as it were, water motion or energy propagation.
So when it curls over there,
yes,
that is, you're saying then it ceases to be just the energy that's moving and the water does actually move. I mean, is it basically that you're trying to conserve the energy, that the energy's got to go somewhere and that it's got to grab the water, basically, isn't it?
Not much energy reflects back out, so most of it has to accumulate. That's why you get the sudden violence of the wave breaking.
Right. Look at that, I love that. Yeah.
It's a wonderful visualization of gentle wave motion becoming violent wave motion, isn't it?
It is. Yeah, you can suddenly up there see it get really, it's vertical and then falls over.
Yes.